The most important idea in this chapter is this one, law of conservation of energy. And this is the statement of the law, and I give you 10 seconds. Think about what we should fill in here. The statement is energy cannot be created or destroyed, but it can be changed from one form to another. This is not just the most important idea in this chapter, this is one of the most important ideas in the whole physics world as well. So that is to say, for whatever kinds of energy that you have, they can only convert into other form. You can't say, oh, the kinetic energy is gone, it disappeared. You can't say that. It must be going to somewhere. So for example, if you try to kick a ball and eventually it stops, so you can say that kinetic energy was high and eventually when it stopped, there's no more kinetic energy. So where does it go? It must go to something. So that could probably be due to friction that the ball will stop, and that will be in the form of thermal energy. Okay, so when we try to do calculation later on, we will be thinking of at a certain time, all the energy that's included in the system add together will equal to another time, again, all the energy add together. So now, here is a link for a simulation video, and I would like to give you 3 questions over here. So go and click the link and try to watch a video while you're trying to answer these questions. So pause the video, go to that video, try the questions, and after that, come back to us.
A few moments later.
One thing you should observe is that if you try to count the number of squares for each energy it has, they will conserve. So that means they will literally convert from one to another without getting more or less in total. So let's have a look here. So originally you have KE with 1 grid, while for GPD you can count 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so 9 grid of, or 9 units of GPE, 1 unit for KE. And when you go down, okay, as you can see, now KE would have 9 units and GPE will have 1 unit. So this is the conversion between GPE to KE. Last question, what happened to the energies and the speed when the car is colliding with the spring? Okay, and there should be a point where it will compress the most and then bounce back. Okay, so here you can see you have 4 grids of kinetic energy. So you have certain speed going forward towards the spring. And then just now when it's really the most compressed, almost, okay, I didn't get the time very right, but then you should be able to see 4 grids of elastic potential energy. Okay, while kinetic energy momentarily to be 0, because all of these KE have been converted into elastic potential energy. And of course, you can't just stay there because the spring wants to bounce you back, right? Like the usual nature. And so that's why this elastic potential energy will convert it back to KE with the same quantity. Okay, as you can see, 4 grids here, because according to this simulation, there's no other energy transformation other than between KE and elastic potential energy. Okay, so here is the wording that I would use. Kinetic energy firstly decreases from 4 units to 0. Okay, and then speed will also decrease because they are just related to each other. Will decrease to 0 where it's the most compressed. Meanwhile, the elastic potential energy would increase to 4 units when it is the most compressed at that only moment. The elastic potential energy after that would decrease when the spring bounces back, and the cart would gained, once again, the kinetic energy back to the original value. And therefore, the speed that when it's leaving is the same as the speed before the collision.
Here comes a new challenger!
Lastly, I want to ask you a bonus question. Just now, we have observed from the visualization or the animation itself that Ke fully, all 4 units converted to elastic potential energy, and afterwards, the elastic potential energy basically returned all 4 units back to Ke. I want to ask you, will this be the same in reality? The answer, of course, is not, right? You cannot get the same Ke, and that means when after you bounce back, it should not be as fast as when the car is going in. You probably would be somehow slower. So I want to ask you, so what happened to the energy then? What is the other energy that is involved here? In reality, along the whole track, there must be friction. So whenever you have friction, you can try, there must be heat. And so that will be the thermal energy that is taking away from the elastic potential energy or the kinetic energy itself. So you have less for Ke at the end. The other one that you may be thinking of, similarly, is the air resistance. So I mean, if you have traveled on a car or riding a roller coaster, you know it's going to be very windy, and so there must be air resistance if you are moving through the air. And so while the air is dragging you, you are also pushing the air as well. So the movement of pushing the air is actually giving the kinetic energy to the air itself, because there will be wind nearby the car, and that's also energy. Lastly, when you try to compress the spring actually will get warmer also. So again, that's also thermal energy. So those will be the sources where it may take the energy away from kinetic energy. So that's why you have less and you get slower at the end. But once again, remember, energy would always conserve. You cannot create or destroy them. If you add up all this energy, it will always be the same amount.